And today the first speaker is Grassi from Geneva. And the title of the talk is Key Formula and String Dualities. So please, Alba, start. Thank you very much for.
Thanks. So yeah, okay. So hi everyone, and so thank you very much first to the organizer for organizing this interesting conference, and then also for inviting me to present some of my work. And so today I basically what I would like to do is to discuss implication of Kyiv formula in the context of string dualities, by focusing on one particular example, which is the topological string spectral duality. And I'm aware that not everyone in the audience is familiar with these topics. So during this talk, I will introduce the various subjects little by little, and hopefully this will be understandable and accessible to everyone. Okay, so this is what I would like to talk about. And most of what I will discuss is actually based on work which I did or that I'm doing together with several fantastic collaborators, which are here. Okay, so let me start maybe by giving a little bit of context and motivation behind what we are doing. And let me maybe start from string theory. Okay, so if we think from a very generic perspective, one of the main forces behind string theory, in some sense, is the fact that string theory provides us with a powerful and consistent theoretical framework to address this very big question, which is unifying quantum mechanics and general relativity. Right? Now, this is a very hard problem, and today that's still an open question. But what we observed during the past few decades is that in trying to really solve this problem, string theorists have generated many new ideas and also very powerful tools, which have given us many new results and application in several fields, like, for example, in mathematical physics. And today I would like to discuss some of these applications. Now, these new results often are a consequence of what we call string dualities. Okay, so roughly speaking, string dualities are a relation between object or theory, which, a priori they look kind of different, right? But sometimes when we look at them from the point of view of string theory, then we can see some hidden connection. Okay, and thanks to this connection, we have many interesting new consequences. And one of the first and also very important example of string duality is mirror symmetry, right? So in this case, we have a relation between two geometries, and the underlying intuition leading to this connection comes precisely from the fact that when we look at the string propagation in those spaces, this propagation is actually identical. Okay. Now, having this type of new connection between these geometries is, of course, beautiful in itself, but it's actually also useful, because sometimes using this connection, we can map very hard problem on one side to much simpler problem on the others. And this type of practical application, in some sense, where we can map something hard to something easier, is something that come up very often in this duality context, and is one of the reasons why we have that many applications. So this was one point. A second interesting aspect is that when we are in this framework, we can also relate some geometrical object, in some sense, to objects which are much more algebraic in a way. And well, one beautiful example of this construction is the work of Witten and Kontsevich, where they were able to relate intersection theory on the moduli space of Riemann surfaces. This is one side, to a matrix model on the other. So when we take this approach, and we will see an example later in this talk, we can even push it and think of geometry itself as some kind of emergent phenomena from a more algebraic degree of freedom, right? And since typically we have a relatively good control over this algebraic degree of freedom, we can use them as a guideline to study the quantum modification to the classical geometrical structure. So we can use duality to learn about quantum geometry. And one example that we will see in this talk, for example, is the example of enumerative geometry. Okay, and in particular, we will see how enumerative geometry emerge from something which is completely different, which are the spectral properties of some quantum mechanical operators. Okay, so this is a second point. A third, also physically important aspect of string duality is the fact that sometimes they can help us to define string theory beyond perturbation theory. Okay, so if we fully want to understand string theory, we need to be able to define this theory non-perturbatively, and string duality can help us also in this context. And a well-known example where this is manifest is the ADS-CFT correspondence of which was first proposed by Maldacena. And also this aspect I will come back. Okay. Okay, so this was just to introduce three important characteristics of string duality, which will come back also later at various stages during this talk. But more concretely, this is what I will talk about today. Okay. So first we focus on one particular type of string model, which is topological string theory on toric Calabi-Yau threefold. So this is going to be our string model. We will consider one particular example of duality, which is the one relating topological string theory on toric Calabi-Yau threefold to the spectral theory of some quantum curve. And also in this case, I will review a little bit this construction. And then what we will do is the following. So in the first part, we will, first I will review Kyiv formula. So we will connect this construction to the framework of Pain-Levé equation. Then I will review Kyiv formula, and we will see how these results that people obtain in the context of Pain-Levé equation can be useful to prove some aspect of this correspondence. Okay, so this is the first part. And then in the second part, we will see how the connection between these topics, so topological string, spectral theory, and Pain-Levé equation, how this connection can be used to learn something new and to obtain some new results in the context of Q-difference Pain-Levé equation. Okay, so this is the plan. So let me start by reviewing a little bit what topological string theory is about. Okay. So one of the main idea in string theory is that essentially we replace point particles. Okay, the fundamental objects are no longer particles, but they are strings, right? So we have some extended object, and formally this can be modeled by considering map from a Riemann surfaces of a certain genus into a target manifold, which I'm going to denote by X. Okay. So let me maybe elaborate a little bit more on this. So first, why Riemann surfaces? How do they emerge in this context? Okay. So Riemann surfaces in this context come into the games when we are considering periodic trajectory of strings. Okay. So, for example, here we have our string. Okay. So these strings propagate, so the time is going this direction. Okay, so it propagates, and then here it's split in two, right? We have two strings at this point which propagate, and then they join and they go back. Okay, so this type of periodic trajectory generate a Riemann surface of genus 2. And well, we have genus 2 because we have one splitting and one joining, right? But in general, we can have several splitting and several joining of our string, and we have genus G Riemann surfaces. Now, the detail of this type of process are encoded in what are called the genus G free energy of string theory, which are denoted in this way. Okay. So these have a path integral representation, for example, and the explicit form of this quantity is what characterizes the type of model that we are looking at. And later we will see what these quantities are for the example of topological string. Okay. And then what we also do usually is that, we have all this diagram which encode these processes, and each diagram is weighted by an appropriate power of the coupling constant, which reflect the number of interactions, right? So here we have the string coupling constant, GS. And we have like one splitting and one joining, right? So the weight of this diagram will be GS squared times F2, so we have genus 2. But then this periodic trajectory, right? This take place in a certain target manifold, right? So we are considering embedding of Riemann surfaces into our target geometry here. And in this talk, we will consider a particular type of target manifold, which are three-dimensional complex manifold. More precisely, we will consider Calabi-Yau manifold. So this is what, roughly speaking, the string framework is about. Now, what characterizes precisely topological string theory is the fact that the genus G free energy encode in a certain way the enumerative geometry of the target manifold. Okay, so topological string theory is basically the physical counterpart of enumerative geometry. And, okay. Okay, so topological string theory are characterized by this genus G free energy here. Okay, so we have a sum which is an infinite sum, but you can prove that this is convergent, so that's absolutely okay. And then we have this quantity. These are numbers. Those are what are called the Gromov-Witten invariants, and what they do basically is that they count in some way holomorphic maps from a Riemann surface of a certain genus into a target space X. Okay, so G here is the genus of the Riemann surface, and D is the degree, because these are maps which wrap cycle in the target manifold, and D is the wrapping. Okay, and then we have e to the minus d times t, and so t is the Keller parameter. It's a geometrical parameter which characterizes our target space. It's like the area of the degree one map. Okay. So basically, this is more or less what topological string theory is about. And for the type of geometries that we are going to consider in this talk, these quantities, so the Gromov-Witten invariant, have been computed explicitly. Okay, so there are various stringy-inspired techniques that allow us to compute this genus G free energy explicitly for the geometry that I will discuss in this talk. Okay, but then what do we do? So what we do typically is that so we define the partition function of our model, which is supposed to be the object that encodes the physics of our system. This is obtained by summing over all possible processes, right? So so here this means that we are summing over all possible genus. Okay. And that's in principle okay, but here we have a problem because so you can compute these FGs as I was mentioning, and you can even estimate how they grow when G is large. And what happens is that they grow factorially, which means that this is a divergent series with a zero radius of convergence. Okay, so this quantity doesn't really make much sense. We cannot plug in some value of the parameter and get a number. Whatever parameter we plug in here, we will get infinity. Okay. Now, this type of asymptotic series appear very often in physics when we do perturbation theory around the small value of the coupling, and typically they are an indication that we are missing some interesting non-perturbative phenomena. Okay, so doing perturbation theory does not capture the full physics of the system, and if we really want to understand our model, we need to be able to go beyond perturbation theory. Okay, so this is the question here. And then, okay, so this is what we can compute, and we can see that it doesn't really make much sense because it's divergent. But then the question that you can ask is, can we define some well-defined function, f or z? So some well-defined function, which is such that this arises only when we do a perturbative expansion around the small value of the parameter. Okay, so this is the question of finding the non-perturbative completion. And one thing that we found in this particular type of topological string model is that indeed we can find this type of well-defined function that reproduce the perturbative expansion of topological string. And the interesting aspect is that this well-defined function actually involves something which is very different, and in particular involve the spectral traces of some suitably constructed quantum mechanical operator on the real line. Okay, and I will be more explicit about what kind of operator we are looking at. Okay, so in finding this answer and in the final result, you see that we have some kind of new connection between, in some sense, different branches of mathematics. On one side, we have enumerative geometry and its physical counterpart, which is topological string. And on the other side, instead, we have the spectral theory of some suitably constructed operators. Okay, so what I'm going to do now is to illustrate this construction in one particular example, and then we will see how Painlevé equation come into the game. So choosing one example here means choosing a target geometry. Okay, so the guiding line example in this talk will be the one where the target geometry is the canonical bundle over CP1 times CP1. Okay, so this is also known as local P1 times P1. And people study this type of geometry a lot, in particular also in the context of mirror symmetry. And in particular, thanks to the work of many people, we can relate this type of geometry to something which look like this. Okay, so this is described by a curve, which is what is called the mirror curve to local P1 times P1, and look like this. Okay, so X and P are a complex variable, right? And M and kappa are the moduli of our curve. Now, when we have this curve, we can associate to that curve an operator. Okay, so the way in which we do that is by thinking here X and P are just complex variables, right? But we can think of them as operator, okay, like in quantum mechanics. Okay, so we promote them to some some operator which have this standard commutation relation where H bar is like the Planck constant, and we will take it to be positive, real and positive in this talk. And if you do that, then you end up with this type of operator. Okay, so this is an operator which acts on the space of function on the real line. And when we act with e to the x, we just have a multiplication like in quantum mechanics, and p instead is like a derivative. Okay, so this operator corresponds to a difference equation of this type here. Okay, when we act on a function on the real line. And then you will have m e to the x plus e to the minus x psi of x. And then we can think of this, basically the quantum version of this is going to be like the eigenvalue equation. Okay. Okay, so this is basically, we have our geometry, we have mirror symmetry, we can write down a corresponding curve, we can quantize this curve, and this is we obtain this operator. Now, this operator has also a meaning in the context of integrable system. For example, this is the Hamiltonian of relativistic dot, right? And this is something that happened very often in the quantization of this mirror curve. They give rise to a relativistic integrable system or cluster integrable system. Now, the operator that actually enter in this construction is not directly this, okay, but it's the inverse. Okay, so we denote the inverse by rho. Okay, and this inverse is something that you can compute explicitly. You can even compute the kernel of the inverse operator very explicitly. And for this example of local P1 times P1, this relativistic toda, this is the kernel that you obtain. Okay. So we have an hyperbolic cosine, and the potential can be written explicitly, and this involves what is called the Fadeev quantum dilogarithm. Okay. And the parameter B, which appear in this expression, is related to h bar in this way. And you can actually show that when x goes to plus or minus infinity, u of x goes to infinity, right? So this is the type of confining potential, which means that this operator has a discrete spectrum, and you can also prove that is of trace class. Right? So the traces of this operator are well-defined quantities. Okay. So we started with local P1 times T1, and this is the operator that we associate to this geometry. Now, when we have trace class operator, we can define the Fredholm determinant to this operator, which is given by this. Okay, so it's basically the product over all the eigenvalue. And the trace class property guarantees that this is well defined, and this is actually analytic in cap. And another quantity which is also related to this determinant that we define in this context are the fermionic spectral traces, okay, which are defined in this way. So here we have our kernel, one of the indices is permuted, right? And then we sum overall permutation. And well, why do we call them fermionic spectral traces? Well, if you fix n, you can show that this is just a particular combination of the traces of this operator. Why fermionic? Well, because physically, if this is the density matrix of a Fermi gas, that's how you would define the partition function. And then you can also show that these two quantities are related, and the relation is given by this. Okay. And again, the trace class property guarantees that this is actually a well-defined convergent sum. Okay. Because this is analytic income. So these are two quantities that we can associate to our operator here. Okay. Okay, so let me just summarize a little bit. We started by considering topological string or better, we started to considering a particular type of Calabi-Yau threefold, toric Calabi-Yau threefold, which is the canonical bundle over P1 times P1. We went through this process of quantization of mirror curve, which gave us this operator. We took the inverse, which gave us this nice trace class operator rho, and we defined the fermionic spectral traces in this way. Okay. Now, the interesting statement is the following. You can study the traces of this operator, okay, in a very quantum regime where h bar goes to infinity, n goes to infinity, but you do that in such a way that this is fixed. Okay, so this is usually, this type of limit are called Toft type of limit. And in this limit, the logarithm of our traces has this behavior here. Okay, so you have a perturbative expansion in 1 over h bar, and then you have some coefficient FGs. Now, the interesting but also non-trivial statement that we can check by explicit computation is that these FGs here, okay, are precisely the genus G free energy of topological string if you consider X as the target manifold. Okay, so this means that you can extract the numerative geometry of this Calabi-Yau, starting from the traces of this type of operator where we have a cosh as an interaction and the Fadeev logarithm in the potential. Okay, so from that point of view, this is a very concrete example where we have geometry, and here a numerative geometry, right, which emerge from the spectrum of some particular type of operators. Okay. Now, when we want to make contact with topological string theory, we have to use a particular identification between h bar and the string coupling constants, which is this one here. Okay, so if we use this identification, then you see that basically this gives us the perturbative expansion of topological string theory that we were writing down a few slides ago. this is a perturbative expansion, right? But at the same time, this is a well-defined non-perturbative object. Okay, so this is the well-defined object that we were looking at, which provide the non-perturbative completion of our string model. And indeed, is such that when you take this limit, you recover the perturbative expansion. But you have more, right? You also have a full tower of non-perturbative correction that you can compute explicitly. Okay. And yeah, so this is more or less what I was mentioning. Okay, so on one side we have topological string and enumerative geometry. On the other side we have this particular type of trace class operator that we can construct via the quantization of curve. Now, one useful point is that the string coupling constant is related to the inverse of the Planck constant. This means that this is a particular example of this weak, strong coupling duality. So we can map hard problem on one side to easier problem on the other side. For example, on the string side, the hard problem is computing non-perturbative effect. Okay, so going beyond the perturbation theory around small value of the coupling constant. But if we map this on the operator theory side, this is like doing WKB method in quantum mechanics. And this is something that we have a relatively good control over, especially because of the connection with Nekrasov-Shatashvili. On this side, instead, what is hard is going beyond WKB. Okay, and but if we use this mapping, non-perturbative effect in H bar, which is what is hard to compute in quantum mechanics, can be obtained by using the perturbative expansion of topological string. So by combining this and this, you can have an exact analytic solution for the spectral theory of these quantum mechanical operators. Okay. And as you know, there are not many quantum mechanical operators that you can solve. Analytically, but this type of operators that arise in the quantization of mirror curve and that have a direct connection with relativistic integrable system, now because of this construction, we can solve them exactly at the level of the spectrum, but also at the level of the eigenfunction. And this is a very interesting follow-up of this construction, but it's not what I'm going to talk about today. Okay. So today I will mostly focus on the connection between this construction and Penley equation. Do you have any questions so far? Okay, so let me now move to a more direct connection with Penley equation. So,
sorry, can I have a short question?
Yes.
To mention that you have some series in T and you take Hooft limit, yes?
Yes, I don't have series, yeah.
In H bar, series in H bar. So how should I think about this function when H bar is going to infinity? So the parameter in which we take expansion, it becomes infinite, right? Or infinitely small, but so I mean about analytical properties of this series.
Yeah, no, so that's yeah. So this is what I was mentioning. This is divergent. It's a zero radius of convergence.
Okay.
Colleague, but do you see that this is not normal but inverse H bar in a sense?
Yeah. I see.
Yes. No, that's the thing. Yes, this is.
It's a bit confusing. I wanted to ask you, but then you explained that your H bar is G string -1. Yeah.
Yeah, this is a series expansion in like 1 over H bar, right? So.
Okay.
Yes.
Okay. Thank you.
Thanks.
So I have to think about this like in a form of expansion. So H bar is like formal parameter here.
Yes, exactly.
And Fg is some good well-defined functions in T.
Yeah.
Yes.
Exactly.
Okay. Thank you.
Thanks.
Excuse me, please. And if I understood correctly, that you can compute the spectrum of this operator or not?
Yeah. So that's another good point. So basically before this construction we couldn't. But now, because of this construction, we can. Okay.
So you can reproduce this half-shutter
yes.
butterfly.
Yes. Actually, so yeah, this is an interesting point. So this goes back to, let me go. So here you see X, I choose as a particular, when I do this quantization, I choose a particular slice of the possible value. So if you want X here, it's really like real in some sense. If I want to get the butterfly, I have to do this, right?
Mm-hmm.
This is a different spectral problem. There are things that we can say about this, but at this moment, not really much. And my talk is not going to be about this slice, but it's going to be about this slice.
And it's kind of continuous spectrum, or?
No, this as a discrete spectrum. This is discrete. If I take H bar to be, let's say, real and positive, and M to be real and positive, is discrete spectrum. If I take M to be 0, it's a different story. But in this talk, M is not going to be 0.
So.
Yeah, so yeah, there is indeed a lot of assumption and specification. Yeah.
And what the spectrum looks like? It's well.
It's going to, yes. So it goes like En goes like so the logarithm of En goes like square root of n, I think, plus some constant. If I correctly, yes. And
okay, thank you.
Yeah. And yeah. Okay, so that's the first part. Okay, so now, as I said, I would like to connect with Pain-Levé equation. Now, to do that, it's useful to formulate this construction at the level of the Freedom determinant of this operator. Okay, so here we were mostly looking at these traces and how we can extract the geometry out of them. But now the object that I really want to look at is the determinant. Okay. So let me maybe go back to our example. This is always this local P1 times P1 geometry. Okay. And for now, let me take the parameters to be like this. Okay. So the reason why I'm taking this parameter is because things become much simpler. And in this case, you can actually show that the determinant of this operator can be simply written in terms of a Jacobi theta function, where the argument can be expressed in terms of Gino-zero Gromov-Witten invariance. And for this type of geometry, this we know how to compute, and the generating series is given in terms of some hypergeometric function. Okay. So we can express this determinant explicitly by using Jacobi theta function and some hypergeometric function. And this is something that you can test in various ways. And okay, now this is this particular example. Okay, but in general we can also construct this determinant and compute this determinant explicitly. It's just that instead of a Jacobi theta function, we have what I would call a generalized theta function. Okay, so we still have this type of infinite sum like in the Jacobi theta function, which is indeed convergent and everything. It's just that what is in the summand for generic value of the parameter is slightly more involved. And so the important point here is that it's not really that we can write the determinant as a sum. This is a bit maybe obvious, is the fact that we can really compute this quantity explicitly. Okay, and this is what is usually called the topological string ground potential. And this is a particular combination of the topological string free energy, but for generic value of the parameter, we don't just have Gino-zero, but we have some more cumbersome combination of all genus. And on the top of that, we have an extra piece which involves what is called the refined topological string free energy in the Nekrasov-Shatashvili So the exact expression of this quantity involve various objects, which I'm not planning to introduce in detail of this talk because we will not really need it. Now, the part about topological string that we review in the first part, the piece about the refined topological string, I'm not gonna review this because then I want to make contact with Pain-Levé equation and Kyiv formula. And for that, we will take a particular limit of this. And in this particular limit, this extra piece goes away. Okay, so let me just mention that is there, if you want the full freedom determinant of the Hamiltonian of relativistic Toda, you need to know what this quantity is. But today we will just make contact with Pain-Levé equation. So we don't really need to know what are the details of this extra piece. Okay, so this is a very precise expression, right? This side we can compute analytically using topological string theory and some refinement. This part we can compute in various ways. For example, if you don't want to use our construction, one thing that you can do on the operator is do a numerical analysis of the spectrum, for example. Okay, so you can, for instance, compute this side numerically, and then see that it matches what's come from topological string theory, and you can do that with hundreds of digits. So I don't have many doubt that this construction is correct, but I think it's important to give a rigorous proof of this type of relation between spectral theory and on the other side topological string. And one way to gain a little bit of intuition for that is by bringing Pain-Levé equation into the story. Okay, and this is what I would like to do now. So what we will see is that there is a particular limit in which both sides simplifies, and in this limit we can recover results that people obtain in the context of Pain-Levé equation, and what we can use what they found to prove this equality, but in this special limit. Okay, so do you have any questions so far? Otherwise, I will go to Anna. Maybe I have to go because I'm a bit late. Okay, so now let me just pause a little bit with Pain-Levé equation and spectral, with topological string and spectral theory, and move to Pain-Levé equation. Okay, this is the third layer of the talk. So Pain-Levé equation are a second order nonlinear ODE with this particular property that the solution are free from a movable trivial point. Right? So we have a second order equation, T is the time, and then we also have some extra blue parameter, like free parameters, okay, which I denoted here in blue, and I'm sure that you are more or less all familiar with this type of equations. Now, an interesting characteristic of Pain-Levé equation is that they can be organized in a confluence diagram. Okay, so this will look like this. Okay, what this means basically is that we can start from this equation, we can rescale the parameter in a certain way, okay, and then we can go from that to all the others. And the way in which this is done is summarized in this diagram here. Now, the aspect of Pain-Levé equation which I am interested in this talk is about constructing generic solution to this equation in a very explicit form. Okay, and this is something that was achieved around 2012 by Gamayu, Yorkov, and Lisovy. And since they were both from Kyiv, this is usually referred to as the Kyiv construction. Now, how do we understand this? So maybe pictorially, we can kind of have an idea of what is going on by looking at these two diagrams. Okay, and I will give a precise example later, but let me maybe now just try to give an idea of what is going on. So here we have the confluence diagram of Pain-Levé equation. Okay, and here we have let's say the coupling diagram maybe in Seiberg-Witten theory. Okay, and also an important point is that, so there is a nice story here, but today I will not talk about that. Okay, so let me just focus on the upper line. So in each node here, we have a particular example of cyber-Witten theory. So the type of theory that appear here are SU2, n equal 2, and they are 4-dimensional. So those are supersymmetric generalization of Yang-Mills. And what changes in each of these parts is the matter content of the theory. Okay. In particular, NF equal 4 means that we have 4 hypermultiplets. So we have like 4 masses. And when we go down, we scale away 1 mass after the others. Okay. And so I should say that this type of parallelism between Pain-Levé equation and 4-dimensional cyber-Witten theory, this was known even before, for example, by the work of Yasuhiko Yamada and various collaborators, and we saw a part of it in the talk yesterday. And so when we use this type of mapping, for example, the masses of the hypermultiplets are mapped to this blue parameter, the free parameter in Pain-Levé equation, and the time is related to the exponential of the gauge curve, roughly speaking. Okay. So what Gamma U, Jorgo, and List realized is that you can use the partition function of this theory, and the partition function is basically the Nekrasov function. You can use the partition function of this theory as the building block to construct solution to all these Pain-Levé equations. And when you change Pain-Levé equation, you change the type of cyber-Witten theory that you compute the partition function of. And now I would like to maybe go into a bit more detail for this example here. Okay, so let me maybe review in this particular example what is one of their achievements. So they were able to write the solution to the Pain-Levé equation in this form here, but it is not the end of the story. Okay, so T is time, sigma and eta here are the initial condition, right? And well, this simply means that you can rewrite the solution Q in terms of the tau function in this way here. And what they were able to do basically is to give a very explicit expression for this tau function. And this very explicit expression can be written in this form here. Okay. So you have a sum over integer, but again, this is like a convergent sum. You have a summand, right? And in the summand, you have a particular shift. Okay. And this Z is given by this. So this is a Barn function. And this B here, this is another interesting function, which is precisely the Nekrasov partition function for which correspond to a certain cyber-Witten theory. And well, the important and the relevant aspect of this function for this talk is that this is a concrete and well-defined object that can be written in this way. Okay. So you have a series expansion around small value of t. Okay, but again, you can prove that this is actually convergent, and this was done by some of the people that I was mentioning earlier. And this Cn of sigma, you can really write explicitly what this quantity here are, and for example, the first few coefficients look like this. Okay. So by using this new special class of function, which people originally introduced in the context of cyber-Witten theory, so by using those functions, you can obtain a very explicit expression for the tau function of Pain-Levé equation for generic value of n and sigma, which are the initial condition. Now, this is for Pain-Levé 3-3, but you can do that also for all the other Pain-Levé in this upper part of the diagram. The only things that you have to do is to change the type of Nekrasov function that you use. But the Nekrasov function for all these theory are well known. Okay. So this is what the Kyiv formula is about in this particular example. Okay, so what does this have to do with topological string and spectral theory? Okay, so before going to Pain-Levé equation, we were looking at this type of identity, right? Where here we had the spectrum of some operator, and here we had a topological string theory. Now, the claim is that if we implement a certain limit on this, equality we can make contact with Painlevé equation. And let me start by this, on this side here. So in this side here, so this is our original operator, right? This is the kernel of the inverse of the Hamiltonian of relativistic Toda. We have to parameterize the quantity which appear in our determinant in a certain way. And in particular, we have to take h bar to infinity. And if we do that, then what we obtain is that the determinant of this operator become another Freedom determinant of another operator, which is much simpler. And the resulting operator is basically this. Okay. So in this scaling limit, the Fadeev dilogarithm simplify, and you're just left with the hyperbolic cosine. And the also nice aspect is that people study this type of operators already in the 70s in the context of Painlevé equation, in particular McCoy and collaborators, and also various other people. And they already show that this determinant solve the Painlevé equation for a particular type of initial condition. Okay, so this is what we obtain on the spectral theory side. On the topological string side, instead, if you implement this scaling limit, you basically recover the tau function of gamma u Yorgov and Lissoby with a particular choice of the initial condition that in our convention is like this. Okay. And then you can check that in those conditions are exactly the same as the one that enter in this work of McCoy and collaborator. This is related to the 2D Ising, right? And then because of unicity of the solution, then you have this identity that you can indeed prove after you take this particular limit. Okay. Now, this was one example. Okay, we fix the target geometry in string theory to be of a certain type, and we fix the type of Painlevé equation. But this you can generalize it also to other geometry and other Painlevé. And the more or less the diagram that you obtain basically look like this. Okay, so let me I'm a bit slow. Okay, so let me maybe try to say a few words about this picture. So here we have topological string on toric Calabi-Yau manifold. Okay, so this two-dimensional Newton polygon, this represent, because thanks to the work of Batiryev and Orivav and all that, to each of these toric geometries, right, we can associate a two-dimensional Newton polygon. So this is, for example, the one that represent local P1 times P1. These are other geometries. Okay. And what we did today is basically considering topological string on this type of geometry, the corresponding spectral theory, and then we saw that in a certain limit, we can make contact with Painlevé equation and via Kyiv formula, for example, also to a particular type of Cyberwitten theory. Yeah, so there should be a lot to say about this diagram, but I'm going to maybe go more directly to the point. So what I would like to do now is to spend a little bit of the remaining time on this corner here. Okay, so what is this corner here? So this is something that we saw already yesterday in the talk of Professor Yamada. So the story goes more or less like this. So already in I think this was the 80s or maybe beginning of 90s, several mathematicians like Ramani, Grammaticos, and then Sakai and many others, they understood that Painlevé equation actually is just part of a bigger picture which include this Q deformed Painlevé equation. Okay, so very roughly speaking, Q deformed Painlevé equation are difference equation which have an interesting analog of the Painlevé property. And well, they are difference equations that depend on a parameter Q, and they are such that when you tune Q to 1 in a certain way, you recover the original Painlevé equation. Okay. And what I would like to do now is to exploit a little bit this picture to obtain some interesting new results in this corner over here. And okay, so this was the plan. Okay, and so far we are here. So let me spend the remaining 9 minutes to discuss a little bit this part. So one interesting result is that basically you can consider the freedom determinant of the operator that arise when we quantize this mirror curve, the mirror curve to this geometry. Okay, so this is exactly the type of freedom determinant that I was discussing earlier. And then the claim is that this freedom determinant solves a corresponding Cuban-Levy equation according to this diagram here. And again, let me maybe illustrate that concretely in one particular example, which is our guideline example, and is the one of local P1 times U1. Okay. So this was the operator, okay, that we got, the kernel of the operator that we got in this quantization. And the claim is that his freedom determinant basically solves this Q-Pan-Levy 3-3 equation, provided we use an appropriate dictionary. Okay, so the Q-Pan-Levy 3-3 equation can be written in this form here. So it's a bilinear difference equation. Okay, and the parameter Q of the Q-Pan-Levy is related to H bar on the quantum mechanical side in this way here. Okay, and if we want to recover the standard Pan-Levy equation, we have to implement precisely this limit that I was mentioning earlier, where among various things we send H bar to infinity. Okay, so when we do that, this will recover a certain form of the Pan-Levy 3-3 equation, and our determinant will, as I was mentioning, will reproduce precisely the Pan-Levy 3-3 solution of the 70s. Okay, so from that point of view, we can think of this determinant of the operator that arises when we quantize the mirror curve to this geometry as a generalization of this whole school result in some sense, the generalization from Pan-Levy to Q Pan-Levy. Okay, and also let me mention just one thing is that, you know, in this picture we have two types of difference equation. Okay, so one is the Q Pan-Levy. This is a bilinear difference equation, and the other one is the difference equation which is associated to this operator. Okay, so this was the inverse of the Hamiltonian of relativistic data. Okay. So you have two types of difference equation, and the claim is that if you take the freedom determinant of the operator associated to this difference equation here, then this solves the Q the form Pan-Levy. Okay. Okay, so this is one interesting result. So by exploiting the connection between these topics, so topological string, the spectral theory of quantum curve, and Pan-Levy equation, we can construct geometrically some new freedom determinant solution to Q difference Pan-Levy equation. Okay, so this is an interesting new result, I think. And so another interesting problem that we can address in this framework is related to the long distance expansion in the context of Q Pan-Levy equation. Okay. Now, to address this problem, I first need to make a step back to the standard Pan-Levy equation. Okay, so this was the Kyiv formula, okay, for the tau function. So this formula is an expansion around small value of t. Okay, so this is like a short distance expansion. This expansion, this sum is convergent and everything, but it's still an expansion at small around t equals 0, right? And then you can ask, can we do something similar around t large, right? So a series expansion in 1 over t. And in the context of the Pan-Levy 3-3 equation, this question was addressed and answered by several people. And what they found is this, okay. So you still have this this type of structure, which is similar to the structure that we had in the Kyiv formula. We have a Barn function, and then we have this, right, which is a series expansion in 1/t, because R is related to T in this way. Okay, so even when you look at large distance, so expansion in 1/t, you can have a similar structure, but there are some differences. Well, one of the differences is that, for example, here, you really know what these coefficients are, right? You can write down an explicit expression in terms of combinatorics of Johan diagram, what Cm sigma is. In this case, instead, at least I'm not aware of a similar expression. So this is one difference. And another difference is the fact that here, you know, we are doing series expansion, but everything is convergent, right? This is convergent. That's not the case here. Okay, so there are several subtleties. Nevertheless, one question that you can ask is, can we generalize this type of structure to a Cuban-Levy equation? Okay, in the case of the Kyiv formula, so the short distance, or small t, this was generalized first by Bernstein and Sheshkin, and then by also, this was for the Pan-Levy 3-3 equation, and this was generalized by various people, probably also in the audience. And then in the same way in which this generalization took place, you can ask about generalization of this. Okay, and again, using insight which come from topological string, and in particular the expansion of topological string partition function around the conical point, you can provide some generalization of this type of structure. But this is still some work in progress. Okay, so I still have 2 minutes, and so let me just very briefly summarize and also conclude. So we have basically 3 main players in this. We had the 3 main players in this talk. One was topological string theory on toric Calabi manifold, spectral theory of quantum mirror curves, and Cuban-Levy equation. And we saw that there are some connection between these 3 topics, and that this connection can actually be used to learn something new in each corner. And this is giving us many interesting new results, and hopefully many more. And yeah, so thank you. I think with this I'm done. And thank you very much.
So thank you, Alba. So questions or any comments? Just well, I'm still amazed by in what you say, that totally complex picture, yeah, and divergent, then sometimes turns into to be very dependent on particular choice of some real slice, yeah, and suddenly it become convergent. And do you have any explanation why it happens?
So let me see. I'm not sure I understand your question.
Okay,
So
that's even maybe not a question, that is some amazement, but say, let me put it as a question, because these formulas like Kyiv formula or Nekrasov formulas, they exist not for all solutions to the equations, while these topological strings seem to exist everywhere.
Yes, you mean like, for example,
why sometimes this totally divergent turns into something really defined, and what are the obstacles for this to be true in general?
Yeah, so you're asking, your question is, for example, about this, right? Here you have local P2.
Yeah, or better to the other side, well, that's also interesting, and maybe you know more about that, but also to the left where you have these points, the same phenomenon happens. There are no Nekrasov functions more.
Yes, there's no Nekrasov function, but for example, here we know what is the equivalent of this, for example. And there is no Nekrasov function. There is something which is similar to Nekrasov function, which is the Kopakuma-Waffa function, but it's not, it's, yeah.
Okay.
It probably is really more about geography. I mean, you see, even in this case, it's true that I don't really know like a gauge theory for that. But yeah, if we think in terms of topological string, that's fine, right? Rather than from 5D.
Okay.
So in this case, probably it's pure C2 with chance Simons at 1, if I understand correctly, what is in that place.
No, probably you are referring to the conifold, Pasha.
Pash, you are saying about another four-dimensional case, yeah? And Alba probably is saying about local P2, it's about triangle.
Ah, wait,
Yes.
I see.
Yeah. So that example, yeah, which is also somewhere above, it's Chern-Simons, yes. Okay. So let's thank the speaker again and make some break. Yeah, till next talk is in 12 minutes. Yeah. Volodya, do you need to test your
Well, maybe